Hi! Today I'd like you to design a back-end system for a digital wallet. Users should be able to transfer money from one wallet to another. Feel free to ask any clarifying questions before proposing a solution. Before jumping into the architecture, I'd like to clarify a few key requirements. Are we strictly focused on wallet-to-wallet transfers? What is our target peak TPS, latency requirement, and availability target? Do we require strong consistency, immutable audit logs, or cross-currency exchange? Great questions. Yes, strictly wallet-to-wallet in single currency USD. We need to support 1 million peak TPS with sub 100 millisecond latency and 99.999% availability. Strict strong consistency is non-negotiable. Zero double spending, and full immutable audit logs are required for compliance. Understood. Based on those constraints, my 4 primary design priorities are: 1. Correctness through strict ACID guarantees. 2. Reliability with high availability. 3. Auditability via immutable logs. And 4. Scalability to handle 1 million TPS. If our target peak throughput is 1 million transfers per second, we can perform a quick back-of-the-envelope capacity estimation. Every single transfer updates 2 wallets, debiting the sender and crediting the receiver. This means we are looking at roughly 2 million balance updates every second. Since no single database instance can handle 2 million transactional writes per second on its own, a single database won't be enough. We will absolutely need to use horizontal partitioning and sharding across our data layer. To start, here is my initial high-level architecture. Requests come in through the API gateway, which handles authentication and rate limiting, and routes to the Wallet API. The Wallet API delegates core money transfer operations to the Ledger service, which writes to an ACID-compliant transaction store. For fast balance reads, the balance service reads directly from read replicas. That makes sense as a starting point. Could you walk me through the step-by-step lifecycle of a transfer request as it flows through these components? Sure. When user A transfers $100 to user B, the client sends a request to the API gateway. The gateway forwards it to the Wallet API, which validates the accounts and balance. Then, the Ledger service starts a transaction. It debits $100 from user A's account, credits $100 to user B's account in the transaction store, and logs the transfer event. Once committed, a success response is returned back to the client. Now let's consider a failure scenario. In a microservices architecture where Wallet A and Wallet B are managed by different database shards, what happens if Wallet A is debited successfully, but the system crashes before Wallet B is credited? That is the fundamental problem with distributed systems. In a single database, a local ACID transaction guarantees atomicity. But across separate microservices or database partitions, a network partition or crash between the debit and credit operations will leave the system in an inconsistent state, effectively losing money. A simple database update isn't sufficient here. We need a distributed transaction protocol to coordinate state across services. Since a simple database transaction won't work across multiple shards, how would you guarantee data consistency across these different database partitions? There are 3 primary options: two-phase commit, try-confirm cancel or TCC, and the Saga pattern. Traditional two-phase commit is too synchronous and holds database locks for too long, degrading availability. TCC reserves funds first before committing, but requires complex application-level reservation logic. For a microservices architecture, I recommend the Saga pattern. With Saga, each step commits locally immediately. If a downstream step fails, such as crediting Wallet B, the Saga coordinator executes a compensating transaction that refunds Wallet A, restoring consistency asynchronously. That makes sense for handling distributed transactions. But suppose our finance and compliance teams need to audit every single transaction made over the past year, or reconstruct a wallet's exact balance at any point in history. How would your architecture support that? To solve auditability and state reconstruction, I would introduce event sourcing. Instead of updating balance rows directly, every incoming transfer request goes to a command queue, passes validation, and is appended to an append-only, immutable event log. State changes are stored as a sequence of events. The current balance is simply a projection computed by replaying these events. Because the event log is immutable, finance gets a complete, tamper-proof audit trail, and we can reconstruct any historical balance by replaying events up to a specific timestamp. Event sourcing provides an incredible audit trail, but if every balance query or API read has to replay millions of historical events from the log, won't that be far too slow for real-time reads? Exactly. Replaying events on every read would create a massive bottleneck. To solve this, I would adopt CQRS, or Command Query Responsibility Segregation. We separate the write path from the read path. The write model appends new transactions to the event log, while asynchronous projections consume those events to maintain read-optimized data stores. For example, a balance projection asynchronously updates a fast read replica for the balance API, while an audit projection updates an analytics store for the finance reporting API. This guarantees sub-50 millisecond read performance without compromising the write log. Putting everything together, here is our end-to-end architecture. The client sends a request to the API gateway, which forwards it to the wallet service. The wallet service invokes the Saga coordinator to manage the distributed transaction across partitioned database shards. In partition A, the debit event is committed to an append-only event log. The Saga coordinator then triggers partition B to log the credit event. Asynchronous CQRS projections continuously consume these event logs to update read-optimized models for instant balance queries. If any partition fails during execution, the Saga coordinator executes a compensating rollback transaction, maintaining complete reliability and auditability at 1 million TPS scale. This is an exceptionally complete architecture. You've effectively combined API gateways, Saga orchestration, event sourcing, CQRS projections, and sharded replication to handle high throughput while guaranteeing strict correctness and auditability. Now let's address horizontal scale. How would your system handle our peak target throughput of 1 million transactions per second without bottlenecking or losing fault tolerance? To reach 1 million TPS, we partition accounts horizontally by hashing account IDs into database shards. Each partition operates as an independent Raft consensus cluster with one leader handling writes and two followers replicating state. We use incremental snapshots and log compaction to keep recovery fast. By scaling partitions horizontally, we distribute the 2 million balance updates per second seamlessly across independent Raft clusters while maintaining fault tolerance. We have a few minutes left. If you had more time or were bringing this digital wallet system to production, what additional trade-offs, edge cases, or system extensions would you focus on? In a production environment, I would prioritize several critical extensions. First, strict idempotency keys across all API endpoints using Redis token buckets to prevent duplicate transfers during network retries. Second, rate limiting and real-time fraud detection services to block suspicious transaction patterns. Third, dead letter queues to safely capture and isolate unprocessor events for asynchronous manual investigation. Finally, I would implement multi-region active-active database replication and comprehensive distributed tracing metrics. To summarize our design, I started by clarifying requirements and calculating our scale at 2 million balance updates per second. I proposed a core wallet service, introduced the Saga pattern for reliable distributed transactions across shards, adopted event sourcing for immutable auditability, used CQRS for real-time read performance, and scaled the system horizontally with Raft consensus partitions. Excellent work, Mei-Ling. You covered correctness, high-throughput scalability, reliability, and auditability while clearly explaining every architectural trade-off. This is a solid production-grade system design.